Right, so microwaves and visible lights are two types of electromagnetic wave. Both can be used for communication, give two properties that are common to both visible light and microwaves. Right, so the first one is they both travel at 3 times 10 to the 8 meters per second, and remember this is in a vacuum. Another one could be that they both refract, they diffract, they reflect. All of these are standard properties of electromagnetic waves, so any of those would be fine. Name two more types of electromagnetic waves that can be used for communication. So we've had visible light and microwaves. So what are the other two main ones? They are radio waves and infrared. Right, Wi-Fi is a system that joins computers to the internet. Microwaves with a wavelength of 12.5 centimeters are used to link computers, and the microwaves travel through air at 300 million meters per second. So we're calculating the frequency here, so we know that V is equal to F times lambda, so therefore F is equal to V divided by lambda. If V is 3 times 10 to the 8, and remember that number, that's going to be really helpful. The wavelength is 12.5 centimeters, so 12.5 divided by 100 is going to give us 0.125. Okay, if we do that, we're going to end up with 2.4 times 10 to the 9 hertz. Okay, if we were to write this out, it would be 2, 4, and we're going to have 1, 2, 3, 4, 5, 6, 7, 8 zeros. Remember that this after the 2 is going to give us our power of 9. Okay. Right, Wi-Fi is used widely in schools, however not everyone thinks that this is a good idea. A politician commented on the increasing use of Wi-Fi. He said, "I believe that these systems may be harmful to children." Suggest what the politician could have done to persuade people that what he said was not just an opinion. Now remember, to be not just an opinion, he would need more evidence. So he needs to provide more or some evidence to support the idea. Okay, why did the group of scientists suggest that there is a need for further research? This would be to provide more evidence. So the more evidence we have, the better it is we can back up any claim. So to provide more evidence, and then we would know if they were really harmful or not. So we're providing more evidence to see if waves are harmful. So remember, the more tests on anything we do, the more reliable our evidence is. Okay? Right, electromagnetic waves behave differently in different situations. It says electromagnetic waves travel at 3 times 10 to the 8 meters per second. Now I know that's quite hard to see, but you should know by now that this is our standard speed for an electromagnetic wave in a vacuum. So all of the waves travel at that speed. Microwave radiation has a wavelength of 2 centimeters. So we know V is equal to F times lambda. So to rearrange for frequency, we do V divided by lambda, and therefore 3 times 10 to the 8 divided by the wavelength, which is 2 centimeters. So remember, there's 100 centimeters in 1 meter. So we're going to do 2 divided by 100, and that will give us 0.02. So we're going to divide that by 0.02, and that will give us 15 billion hertz. Okay, so again, it would be better if we did this in standard form. So how many numbers have we got after the 1? Well, we're going to 1.5. I'm going to count this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to do times 10 to the power of 10 hertz. So remember, we count the numbers after the first digit. Right, some students did an investigation to study the behaviour of waves, and this is shown in a ripple tank. It says complete the wavefronts on the figure. Show how the wave is refracted as it passes from the shallow region into the deeper region. Okay, so what I would always advise you to do is to continue these waves on until it hits this region here, and they need to be at the same wavelength. Now, when we do this, we're going to put a line down the center, and this is going to enable us to work out some angles. So the first thing we need to do is put a normal line where we've got this region here, and the normal line is always going to be at 90 degrees to the object, so it needs to be this dotted line at 90 degrees. Okay, now with a different pen I'm going to show you the angle. This is the angle that we're looking at, and waves in deeper water actually speed up. So in the deeper region the waves are going to speed up. So if the waves speed up, that actually causes the wavelength to increase. Now, if you remember in a block, when the light hits the block, and I draw the line for refraction, when it enters the block it's going to refract towards the normal line. So that angle there is going to be smaller than that angle there. When it leaves the block, it's going to refract away. So in this particular case, just like here, when it goes from a solid to a gas and speeds up, when the light speeds up, it refracts away from the normal line. So the same is going to happen here. It's going to refract away from the normal line. So what we're going to get here, we're going to get a bigger angle than this one. So we're looking for this angle here where we're going to draw a line like this, and you can see that that angle is bigger than this angle. Now we've got an angle, this is why I drew this line in the first place, we can now put our wave fronts at 90 degrees. So you can see that these are all at 90 degrees to my line. This is why I've drawn that line. So these wave fronts have got to be at 90 degrees as well. So we're going to draw those wave fronts at 90 degrees. Okay, so probably not the best, probably about there. You can see these wavelengths are larger than those ones, and you can see that this is at 90 degrees. So that's how you're able to draw the diagram properly. Okay, so that's how we would draw it. Explain what happens to the waves as they pass into the deeper region. Well, remember I said that waves in deeper water actually speed up. If the waves speed up, the wavelength increases. Okay, now the frequency during refraction actually doesn't change, so the frequency is constant. So frequency is constant. Now I'm just going to do a bit of explaining here. This is not really answering the question, it's just helping to explain something. So the frequency is constant, and we know V is equal to F times lambda. F is equal to V divided by lambda. So if this is constant, then if we change one of these, we have to change the other one. So let's have a look. Say we change the wave speed. We just talked about the wave speed increasing as it goes into deeper water. So if I increase V, what would I have to do to the wavelength? Well, that would always have to increase as well for F to remain constant. So just to show you this, say we had 10 is equal to 10 divided by 1. If I increase my velocity to 100, for it to still equal 10, I'd have to divide it by 10. So you can see by increasing that by a factor of 10 means I have to increase that by the same factor for this to remain constant. So as the water speeds up, the wavelength will increase by the same amount. Okay? Right, the waves generated on the surface of the water are transverse waves. Describe the difference. Now this is something you should definitely know by now. So transverse, the oscillation, remember that, which is the vibration, the oscillation is perpendicular at right angles. It is perpendicular to the direction of energy transfer. Remember, all waves transfer energy. For a longitudinal wave, we'll just go back to the red pen. For a longitudinal wave, the oscillation is parallel. Remember, these are the key terms, parallel or perpendicular. The oscillation is parallel for a longitudinal wave, and it is parallel to the direction of energy transfer. So that's really important that you remember these two terms. Now, while we're talking about longitudinal waves, a good example is sound. When we're talking about transverse, they are all electromagnetic waves. So light, but remember they're all electromagnetic waves, from radio waves right through to gamma. Right, some students investigate the properties of waves generated in the figure above. Student A says the waves move water from one end of the tank to the other, and student B says that's wrong. Only the waves move, not the water. Well, in a transverse wave, if you remember, we've got this wave moving up and down, but actually what's happening is we're getting this oscillation. So the water particles are moving up and down, but the energy is traveling from left to right. So we should know that B is correct, but how could we check this? Well, if you think about in the sea, you can have a buoy that floats on top, and it may be tethered or to a little weight, etc. And what does that do? It will bob up and down. So we could use a water buoy or some floating device, and what will it do? It will move up and down, it will bob up and down if the waves move and not the water. So this would prove the idea. So when you watch things like buoys in the water, they just bob up and down, and the energy is carried from here to here. So the energy is moving perpendicular to the oscillation of the wave, and this happens on the surface of water. So water has surface waves that are generally transverse, and under the surface you may get longitudinal waves. Right, another student uses a ripple tank where all the water is the same depth. She measures the wavelength of each wave as 0.34 meters, and the period of each wave is 0.42 seconds. Calculate the speed of the wave. So remember, V is equal to F times lambda. We know the wavelength is 0.34, but this time we've got a period. So that is the time taken for a wave. So remember that our time period is equal to 1 divided by frequency. And frequency is equal to 1 divided by time period. We can just interchange these. So if we know frequency is equal to 1 over time period, then we can just do 1 divided by 0.42, and that will give us the frequency, which is 2.38 hertz, and we're going to multiply that by the wavelength, which is 0.34 meters, and that will give us our wave speed of 0.81. The units are in meters per second. Right, visible light travels through air at 300 million meters per second. Remember, this is 3 times 10 to the 8. Why can we assume that radio waves travel through air at the same speed? Well, all EM electromagnetic waves travel at 3 times 10 to the 8 meters per second in a vacuum. So we could assume that they should be the same in air. So we could assume same speed or velocity in air. Right, a radio station broadcasts at a frequency of 200 kilohertz. So that means 200,000 hertz. We're trying to work out the wavelength this time. We know V is equal to F times lambda, and lambda is the wavelength, so it's V over F. So we move that up here. We've got a wave speed, which we don't know, but we know it's 3 times 10 to the 8. It's not in the question, but we have to know that anyway, and we know that's divided by 200,000. So if we do that, we will get 1500 meters, and that always looks about right because we know wavelengths can be up to about this kind of length. Right, draw a vertical line on the diagram to show the position of this radio wave. So if we just have a look at the diagram, we've gone from 10 to a scale of 1000, so that must be 10, and that must be 100. If that's 1000, that must be 10,000. If that's a million, then that must be 100,000. So we're going to put it onto this scale, roughly about here. Okay, so it's closer to the 1000, a lot closer than it would be 10,000. So I'm putting it after the 1000, but make sure you draw a straight line. Right, explain why refraction has not occurred at point X. Well, if you look here, it's following the normal line. So for question 5, you can see the ray of light is following the path of the normal line. So when you follow the path of the normal line, no refraction will occur. The reason for that is these wave fronts will all meet the boundary at the same time. So that means they will all speed up at the same time and they will bunch up and you'll get a reduced wavelength. So just to make that a bit clearer, we would have a larger wavelength and then they would hit the boundary and then they would start to bunch up. But they all bunch up at the same point. So if all the wave slows down at the same point, then no refraction occurs. But you just need to know that it is following the normal line. So when the wave, the light, follows the normal line, no refraction occurs. So follows normal line, no refraction occurs. Right, the name of the process which occurs at Y is called total internal reflection, but this is not on the exam, so we don't really need to go through this answer here. It used to be on the old specification. Right, which of the waves A, B or C is in infrared? Well, we know this is visible light, and out of the 4 wavelengths we're going to have radio waves, microwaves, infrared and visible light in that order. So which one's going to be the biggest one? Well, we know that's radio waves, so that must be this one at 1.1 kilometers. The next one is which one is the smallest out of the rest of these? Okay, so we know that visible light is 0.005 millimeters. So the next smallest, 100 meters, is microwaves. And then after that, smaller than that is going to be infrared. So the one that is infrared is C. Right, a TV broadcasts at 500,000 kilohertz. So again, we have to convert this into hertz. We know 500,000 kilohertz is 500 million hertz. And that's 300 million meters per second. So because there's so many zeros, we're just going to count them and put this into standard form. So we've got 1, 2, 3, 4, 5, 6, 7, 8 zeros after the 5. So that is 5 times 10 to the 8. Just as we know that this is 3 times 10 to the 8. You should have learned that by now. So V equals F times lambda. So therefore lambda is equal to V over F. Our wave speed is 3 times 10 to the 8, and we're going to divide that by 5 times 10 to the 8. Now, because these are the same, they can just cancel out. So we're doing 3 over 5, and 3 over 5 is 3/5, which is equal to 0.6 meters. Right, what happens when a metal aerial absorbs radio waves? So if you remember, if we have a transmitter, then you can run an alternating current which goes through this transmitter, and if you put a current through a wire, you will get a magnetic field around the wire. Remember, so if we have a current going this way, then we would have a magnetic field which goes around the wire. And that magnetic field, being a changing magnetic field, because it is AC, you're going to create a electromagnetic wave, a radio wave. So that radio wave is then going to pass along, and when it comes in contact with an antenna or an aerial, the wave is going to cause the electrons in this wire to start moving, and they will move or oscillate with the same frequency of this wave. So we've created an electric current, that's created an electromagnetic field. The field has then moved through the air to the aerial, and that is then oscillating the electrons in the aerial with the same frequency of the wave, and then that creates a current, and the current is going to oscillate up and down because it's an AC current. So if we look inside this aerial at a wire, you'd have electrons moving up and moving down at the same frequency as this wave. So what happens when a metal aerial absorbs radio waves? The electrons oscillate, which remember means vibrate, so the electrons oscillate at the same frequency as the radio waves. What's that going to do? It's going to produce an AC current, and that AC current is going to be at the frequency of the oscillating wave. Right, stars emit all types of electromagnetic waves. Telescopes that monitor X-rays are mounted on satellites in space. Why would an X-ray telescope based on Earth not be able to detect X-rays? So if a question like this comes up and we put something in space to detect something, it means that the atmosphere is absorbing part of the spectrum. So that is telling you that X-rays are absorbed by the atmosphere. Radio waves and microwaves are two types of electromagnetic wave. Both can be used for communication, and they both travel at the same speed through air. Give two more properties that are the same for both radio waves and microwaves. So again, you need to know that they refract, they reflect, they diffract, they travel through a vacuum. So you have to learn these standard properties for all electromagnetic waves. What is the property of microwaves that enables them or allows them to be used for satellite communication? Well, remember, if this is the Earth and we have the atmosphere surrounding the Earth and we have some kind of satellite up in space, microwaves are able to pass through the ionosphere. Remember, radio waves will reflect off the ionosphere. So microwaves can penetrate the ionosphere. Right, electromagnetic waves travel at 3 times 10 to the 8. Again, the more we see this, the more likely you are to remember it. And they have a wavelength of 2.5 times 10 to the 2. Now I know that's hard to see, so it's really important that when you're doing this, you've printed off the questions so you can see these clearly. Right, V is equal to F times lambda. We should know these off by heart by now. So F is equal to V over lambda, and therefore 3 times 10 to the 8 divided by 2.5 times 10 to the 2. What will that equal? It will equal 1,200,000 hertz. So again, with this, what we could do is say that that is 1.2 gigahertz. Sorry, that's not right. That's 1.2 megahertz. It's a million hertz, not a billion hertz. Or we could say that it is 1.2 times 10 to the 1, 2, 3, 4, 5, 6 hertz. Okay, so that's, and that would make more sense. Rather than writing this big number down, we're more likely to get a better score if we write it in either standard form or we use the correct prefix. So remember, if we started with hertz, then going up, we would then go to kilohertz, and then we go to megahertz, and then we go to gigahertz. So this is to the power of 12. To the power of 9, to the power of 6, to the power of 3. Okay? Right, electromagnetic waves form a continuous spectrum with a range of wavelengths. What is the approximate wavelength of electromagnetic waves? Well, roughly speaking, they can end up at about 1,000 to 10,000 meters. So the largest radio waves are around 10 to the 4, and they go as low, so as small gamma rays are incredibly small, so they go into that particular region. Give one example of infrared waves being used for communication. Well, remember they're used in remote controls. And a mobile phone network uses microwaves to transmit signals through the air. The microwaves have a frequency of 1.8 times 10 to the 9. So I'm sorry, this is really hard to see. And the speed, well, we should know that is 3 times 10 to the 8. So we're after the wavelength. Again, V equals F times lambda. So lambda is equal to V divided by, by F. V is 3 times 10 to the 8. And we're going to divide that by 1.8 times 10 to the 9. What will that equal? Just make that easier and clearer. That's going to equal 0.16666, etc. recurring. So we're going to do this to two significant figures. So we're looking for the two digits here. So that's those two. But because there's a 6 after the 6, it's going to be equal to 0.17. So that is to two significant figures, 0.17 meters. Right, the last question. Some scientists suggest there is a possible link between using a mobile phone and male fertility. The results of their study are given below, and as you can see, 86 sperm count goes down to 69, to 59, and then to 50. So there's clearly a decrease in the number of sperm counts in millions per centimeter cubed. The results show a negative correlation. The more hours a mobile phone is used each day, the lower the sperm count. However, the results do not necessarily mean using a mobile phone caused the reduced sperm count. Could you give a reason why? Well, we are not certain that the mobile phone is the only factor that has affected sperm count. So there may be other factors. So to be certain of things like this, you need, well, you're never going to be certain, but to increase the reliability, you would need a bigger sample size. So bigger sample size required to increase reliability. So in this particular question, it's out of 1 mark, but I just wanted to make this point because if it was out of 2 marks, that's how you would increase the reliability of your investigation. If you want the data to be more reliable, you do it more times, more tests, more reliable. Right, so all the answers to the questions are coming up.